Hello student, today we are going to discuss about one another direct method for finding the solution of a system of a linear equation known as a Gauss-Jordan elimination method. This one is a modified version of a Gauss elimination method. So in this lecture, first of all we discuss about a theoretical aspect of a Gauss-Jordan method and how this one is a different from the Gauss elimination method, and solve one numerical example using the Gauss-Jordan elimination method. So let us discuss about a theoretical aspect of a Gauss-Jordan elimination method. So for sake of a simplicity, here only we consider the three equation, means a system of a linear equation having a three equation and three unknown. For sake of a simplicity, you may also extend this one for the n unknowns and m equations. So for sake of a simplicity, only we consider the three equation in a system of a linear equation. First equation is a a11 x1 plus a12 x2 plus a13 x3 equal b1. Second one is a a21 x1 plus a22 x2 plus a23 x3 equal b2. a31 x1 plus a32 x2 plus a33 x3 equal b3. Suppose this one is a system of a linear equation having a three linear equation. Now we try to solve this system of a linear equation with the help of a Gauss-Jordan method. So what's happening in a Gauss-Jordan method? In a Gauss-Jordan method, we convert the coefficient matrix A into a diagonal matrix, while in a Gauss elimination method, we convert the coefficient matrix A into a lower triangular matrix. But here we convert the coefficient matrix into a diagonal matrix. So how we convert? So first of all, we write a matrix form of this system of a linear equation. So what is the matrix form of this system of a linear equation? So first of all, we write a matrix form of a system of a linear equation. Matrix form of system of a linear equation. System of linear equation. Linear equation. So just we write a what? Coefficient of x1, x2 and x3. So this one is a a11, a12, a13, a21, a22, a23, a31, a32, a33. This one is a coefficient matrix of x1, x2 and x3. So here we write a and then we write unknowns x1, x2 and x3. So this one is a capital X equal, here we write a b1, v2 and v3, and here we write a v. So what is the equivalent matrix form of a system of a linear equation? Ax equal b. Now next one, we write a augmented matrix. Augmented matrix. So augmented matrix of a system of a linear equation. Augmented matrix. So what is the augmented matrix? Just we write a matrix A, partitions, then write a matrix B. So this one is a what? This one is a augmented matrix. So, here we write values of this one. What is the A? A is A11, A12, A13, A21, A22, A23, A31, A32, A33, then partition, write a matrix B. What is the matrix B? Matrix B is a B1, B2 and B3. So, here we write what? Here we write a B1, V2 and V3. So, in a Gauss-Jordan method, first of all, we normalize the first pivot row. So, to normalize the first pivot row, first of all, we choose the pivot row and pivot elements. So, in a first stage of elimination, we choose the common element of a first row and first column become a pivot elements. So, what is the common element of a first row and first column is a A11. So, what is the pivot row? So, first of all, in a Gauss-Jordan method, we choose the pivot row and pivot elements. So, what is the pivot elements here? Pivot element equal what? A11, and it must be necessary A11 does not equal to 0. A11 does not equal to 0 until A11 does not equal to 0, otherwise we unable to apply the Gauss-Jordan method. So, ensure that pivot element does not equal to 0, or not a very small in comparison of all other element of a first column. So, A11, A21, A31. So, we interchange according to the partial pivoting and complete pivoting. Here I am not going to discuss about a partial pivoting and complete pivoting, only we ensure that pivot element does not equal to 0. So, if A11 does not equal to 0, then we perform the normalization in a pivot row. So, here pivot row is a pivot element is a A11 and pivot row is a first row. First row, or you may also say first equation is a pivot equation, or pivot row is a first row and pivot element is a A11 and we ensure that A11 does not equal to 0. Now, we normalize the pivot row, or you may in other words say we normalize the first equation. So, in a first stage of elimination, we first normalize the first equation. In a second stage of elimination, we normalize the second equation, and in a third stage and onwards, we normalize the third and onward equation. So, in a first step of a first stage of elimination, we normalize the first row, which is a pivot row. So, for the normalization, we divide whole row by the pivot element. We divide the whole row by the pivot element. So, after this one, we normalize. You may also say this one is a what? This one is a first step, first stage of elimination, first step, and second step, normalized the pivot row using the transformation, using the row transformation, R1 tends to 1 by A11 R1, means we divide the whole row, means the first row, by the pivot element by the A11. Now, the suppose resultant augmented matrix is this one, resultant augmented matrix is this one, A, partition matrix B. Now, after dividing the A11 in a first row, the pivot element become 1. So, in a normalized form of a equation, in a first equation, the coefficient of a x1 must be equal to 1. So, if we divide by the A11, then this becomes suppose 1 and this become A12 dash. A12 dash means we change the value of A12 in a one time. Similarly, A13 change in a A13 one time and partition change in a B1 one time. This one is the meaning of this notation A12 dash, A13 dash and V1 dash, and there is a no change in a second row. So, A21, A22, A23, similarly A31, A32 and A33, and here B2 and B3. So, after normalization, we perform the elimination. We perform the elimination of a x1 from all other equations. So, how we eliminate the x1 from the all other equation means we equate the coefficient of a x1 from all other equation equal to 0. So, in a second equation, what is the coefficient of a x1? A21. So, we try to convert the A21 equal to 0 and A31 equal to 0 with the help of a row operation to eliminate the x1 from all other equation except the first one. And we repeat this procedure in a second stage of elimination, in which we eliminate the x2 except the second equation and in a stage in a third stage elimination, we eliminate the x3 from the system of a linear equation except the third equation. So, now we perform the first stage elimination and we try to eliminate the x1 except from the first equation. For this one, we equate the coefficient A21 equal to 0 and A31 equal to 0. We try to convert A21, not equate, we try to convert A21 equal to 0 and A31 equal to 0. For this one, we perform the following operation. We perform the following operation means we perform the operation on a R2 tends to R2 minus A21 here, A21, we subtract this row by multiplying the A21 in a pivot row. So, only we perform the multiplication means a division only in a pivot row, not any other row. So, what will happen here? R2 minus A21 R1 and R3 tends to what? R3 minus A31 R1. So, here one thing need to means a focused means only we perform the multiplication and division only on a pivot row. This one is a what? This one is a pivot row. Pivot row. Pivot row. Pivot row. Pivot row. So, we subtract the second row by multiplication of a A21 in a pivot row. Subtract R3 with R1 by with the multiplication of a A31. Now, what will happen? What is the reduced augmented matrix Now reduced augmented matrix become what? This become A and this one is a B. Now what is the reduced augmented matrix? There is a no change in a normalized form of augmented matrix 1, and this one is a A12 dash, A13 dash, and here this one is a B1 dash. Now this one become what? After performing this row operation, this becomes 0 and this become A22 dash, means there is a change in our original value of A22 one time. So this one is a A23 dash and this one is a B2 dash, and similarly if we perform this row operation, this becomes 0 and this become A32 dash, A33 dash and V3 dash. Now again we choose what? We choose the pivot elements. Now in this stage, what is the pivot element? Now here normalization, we perform the normalization in each stage. So here we perform the normalization. For normalization, what we will do? For the normalization, first of all we choose the pivot elements. Now pivot elements in a second stage of elimination, the common element in a second row and second column, this one is a A22 dash. So pivot element is a A22 dash, A22 dash. Now which one is a pivot row? Second row is a pivot row. So for the normalization, we perform the row operation in a second row. R2 tends to 1 upon A22 dash R2. Pivot element is a A22 dash and pivot row is a, here we write a pivot row also. So because R2 is a what? Pivot row. Pivot row is a R2. Pivot row is a R2. So after performing the normalization, means we divide the second row by the A22 dash. If we divide the A22 dash, we divide the second row by the A22 dash, then this element means a diagonal, second diagonal elements become 1. Now what is the equivalent? Augmented matrix. So this become A, V, this one equal 1, A12 dash, A13 dash, V1 dash. Now this becomes 0 and this become 1. There is a one another change in a A23. So A23 double dash, V2 double dash, and this one is a 0, A32 dash, A33 double, A3 dash, and this one is a V3 dash. So this one is a what? This one is augmented matrix after normalization of a second equation. So now we perform the elimination of a second stage elimination, means we eliminate the second variable. We eliminate the second variable from all other equation except the second equation. So for the elimination of a second variable from all other equation, means from all other rows, or you may say all other equations. So what we will do? We will do means we convert the A12 dash and A32 dash equal to 0 using the row operation. So for the elimination, now this one is a elimination stage, elimination, second stage elimination. So in a second stage elimination, we try to convert the A32 dash equal to 0 and A12 dash equal to 0 with the help of a pivot row. And which one is a pivot row? Second one is a pivot row. So we perform the operation on a R1 tends to what? R1 minus what? R1 minus A12 dash R2, because R2 is a what? R2 is a pivot row. Only we multiply or divide in a pivot row only, not in any other row. So, what is the value of R3? R3 tends to R3 minus what? We multiplied by A3 2 dash. A3 2 dash in a what? In a R2. Then what is the equivalent matrix? Now, equivalent matrix become what? Now, equivalent matrix in a next step we write, in a next page we write a equivalent matrix. So, what is the equivalent matrix here? A V equivalent augmented matrix, you may say equivalent augmented matrix. This one equal, here we write a 1, and also there is a change after performing this operation R1, there is a change in a A12 dash, and this become what? This becomes 0, and after performing this operation this become 0. So, what is the element of a first row? First row become 1 0 0 and second row becomes 0 1 0, the second column. Now, what will happen in the third column? Here A13 change one time more. So, here we write a A13 double dash. So, here we write a A13 double dash, and here we write a what? Here we write a A23 double dash, A23 double dash, A23 double dash, and next one is a A33 double dash, A33 double dash, A33 double dash, and here we write a V1, V2 and V3. This one is also a double dash, means the original value of a change, original value of a V1, V2 and V3 change 2 times. Now, again we perform the normalization, third stage. Now, we perform the normalization. So, for the normalization, what we will do? First of all, we choose the pivot element for the third stage of elimination. So, what is the pivot element? In case of a third stage of elimination, the common element in a third row and third column. Which one is a common element in a third row and third column? A33 dash. So, pivot element is a become what? A33 double dash. So, to normalize the third equation or third row, we divide the pivot row by the pivot elements. So, what is the pivot row? Pivot row is a third row, means a R3 with a pivot row. So, how we normalize this one? So, we perform for the normalization, we perform the operation R3 tends to 1 upon A33 dash R3 for the what? For the normalization. Now, after the normalization, what is the equivalent matrix? A, V equivalent matrix become what? There is no any change after the normalization in a first row 1 0 A13 double dash V1 double dash, and there is no change in a second row after normalization in a third equation 0 1 A23 double dash V2 double dash, and we divide the third row by the A33 dash, and in each step we ensure that this one does not equal to 0. This one does not equal to 0. Because at any stage, if the pivot element equal to 0, then we unable to apply the Gauss-Jordan method, as well as also we know that we unable to apply the Gauss elimination method. So, here what will happen? This becomes 0, this becomes 0, because by dividing the A33 dash there is no any change. 0 by A33 dash becomes 0, 0 by A33 dash becomes 0, A33 dash divided by A33 dash, then this become 1, and there is a one another change in a V3, and here we denote this one by the V3 triple dash. Now we perform the third stage elimination. Meaning of this one is a third stage elimination. We eliminate the variable x3 from the first and second equation, or you may say in general we eliminate the x3 means a third variable except third equation from all other equation, means we eliminate the x3 from all other equation except the third equation. So here in a elimination process, during elimination we what which type of a row operation we perform? We perform the row operation here on a R1 and R2. So we perform R1 tends to what? R1 minus A13 double dash R3, and R2 tends to R2 minus A23 double dash R3. This one is a what? This one is a elimination, third stage of elimination. Elimination in third stage. Third stage, or you may say elimination in third stage, or you may say elimination of a third variable. Elimination of third variable. Elimination of a third variable. Now, after performing these two row operation, now equivalent matrix become A, B, this one converted into a 1, 0, 0, and this one become B1 triple dash, and this one become 0, 1, 0, V2 triple dash, and this one becomes 0, 0, 1, V3 triple dash. Now we able to convert the coefficient matrix A into a diagonal matrix. Coefficient matrix A into a diagonal matrix. Now we write a reduced form of a system of a linear equation. Reduced form of a system of a linear equation means we here write the reduced form of a system of a linear equation with the help of a reduced augmented matrix. So what is the reduced form of a system of a linear equation? Here we write matrix A 1 0 0 0 1 0 0 0 1. Here we write a what? What are the unknown? x1, x2 and x3. x1, x2 and x3. So here we write a what? Here we write a x1, x2, x3, and this one equal B1 triple dash, B1 triple dash, B2 triple dash, V3 triple dash. So what is the solution of a equation? Now after the elimination, there is no need of a back substitution. There is no need of a back substitution. This one is the advantage of a Gauss-Jordan method. In a Gauss elimination method, first we perform the elimination and try to convert the coefficient matrix A into a upper triangular matrix. Then we perform the back substitution. But in a Gauss-Jordan method, as earlier we say that Gauss-Jordan method is a modified version of a Gauss elimination method. So Gauss elimination method, there are two steps, forward elimination and backward substitution. But in a Gauss-Jordan elimination method, there is only a forward elimination, and try to convert the coefficient matrix into a diagonal matrix. But in a Gauss elimination method, we try to convert the coefficient matrix into a upper triangular matrix. So here we directly write the what is the solution after the elimination. What is the solution? Solution is a x1 equal b1 triple dash, x2 equal v2 triple dash, and x3 equal v3 triple dash. So this one is a what? This one is a Gauss-Jordan elimination method. Now what is the summary of a Gauss-Jordan elimination method? In a Gauss-Jordan elimination method, first of all, for a given system of a linear equation, here we assume that the given system of a linear equation have a solution and that solution is a unique solution. So I am not talking about the given system of a linear equation having a no solution or many solution. Here only I am talking about a given system of a linear equation having a unique solution. Then we write a given system of a linear equation into a matrix form of a system of a linear equation. Once we write a matrix form of a system of a linear equation, then we write a augmented matrix by combining the matrix A and B. Then we we perform the normalization. First we choose for the normalization, first of all we choose the first pivot element, and first pivot element is a common element of a first row and first column. And which one is a pivot row? First row is a pivot row. Then we perform the normalization in a first row. For normalization we divide the first row by the pivot element, and in a first row what is a pivot element? A11, meaning of this one we divide the whole row by the A11, then the first element of a first row become 1. So in a normalization process we try to convert the coefficient of a x1 in a first equation 1, in a x2, in a second equation x2 the coefficient of x2 equal 1 and x3 equal 1 in a third stage of elimination. So before elimination we perform the normalization, then we perform the elimination. How we perform the elimination? We perform the elimination here, we perform the normalization, then we perform the elimination. For the elimination always remember only we multiply or divide or something else only in a pivot row. We subtract other row by the pivot row and only we multiply or divide in a pivot row, not any other row. Here if you will see here, R1 tends to R1 minus A12 dash R2. Here pivot row is a what? Pivot row is a R2. So only here we multiply by A12 dash or A32 dash in a pivot row. So here other row on a means you may say this one is a first element of a subtraction, this one is a second element. So first element is the other row and second element is a pivot row with some multiplication and division. So after elimination of a first variable in a first stage means we convert the A21 and A31 equal to 0. We repeat this process in a second stage as well as in a third stage. So after forward elimination, once we complete the forward elimination, then the given system of a linear equation reduced in this form, the matrix A, modified matrix A converted into a diagonal matrix, this one is a X and this one is a modified value of a B, and here B1 triple dash, B2 triple dash, B3 triple dash, meaning of this one is there is a change in a original value of a V1 in 3 times, original value of a V2 in 3 times. Then we directly write the values of x1 equal what? B1 triple dash, x2 equal B2 triple dash and x3 equal B3 triple dash. So what is the summary? First of all, we write a given system of a linear equation as a matrix form of a system of a linear equation, then write the augmented matrix, then we choose the pivot element, and first pivot element is a common element of a first row and first column, or you may also say the coefficient of a x1 is a first pivot element and first row is a pivot row. Then we normalize the first row by dividing the first row by the pivot element. Once we normalize, then we perform the row operation to eliminate the coefficient of a x1, or we eliminate the variable x1 from the second and third equation, second, third onward equation, and we repeat this process for the normalization and elimination of a second variable, and similarly third variable, and if there is a n variable, then similarly for the n variable. Now once again I summarize, means what is the difference between Gauss elimination method and Gauss-Jordan method. In a Gauss elimination method, means what is the advantage and disadvantage of a Gauss elimination method over Gauss-Jordan method and Gauss-Jordan method over Gauss elimination method. In a Gauss-Jordan method, we only perform a one step, means a forward elimination, and convert the coefficient matrix A into a diagonal matrix. But in a Gauss elimination method, we find the solution in a two step. In a first step, we perform the forward elimination and try to convert the coefficient matrix into a upper triangular matrix, and in a back substitution we try to find out the solution. But in a Gauss-Jordan method, there is no any step of a back substitution, means of one step we reduced in a Gauss-Jordan method. But what is the drawback of a Gauss-Jordan method? The computational efforts that required in a Gauss-Jordan method is greater in comparison of a Gauss elimination method. That is why always any researcher or mathematician not prefer the Gauss-Jordan method, because computational effort is more in comparison of a Gauss elimination methods. Means there is a more number of a multiplication and division in a Gauss-Jordan method in comparison of a Gauss elimination method, means computational effort is a more in a Gauss-Jordan method. That is why the researcher and mathematician does not prefer the Gauss-Jordan method over Gauss elimination method. But what is the advantage? Advantage is that there is no any back substitution step in a Gauss-Jordan method. So this one is all about this lecture. Thank you watching my lectures. Thank you.